HEXAMERS in superconductivity of ruthenium phosphide, or rather, it's actually a question whether those fluctuations are actually important for superconductivity. So, to begin with, I would like to acknowledge the funding agency, which in this case is majority US Department of Energy, and also my colleagues who contributed to this work. The samples came from Chedrin and Petrovich's group. So in principle, to make a general statement, the emergence of technologically relevant quantum orders and the rich physics stems from complex interaction of electronic charge spin and orbitals and their coupling to the lattice. In many materials, complexities of ordered states at low temperature are explored extensively, but much less is known of what happens in the temperature in the phase space away from the ordered regimes. We are particularly concerned about whether there is actually nanoscale symmetry breaking in this regime. And in experimental world, many techniques are actually not very sensitive to the nanoscale simply because they average over the bulk. So when electronic properties coupled with lattice, it's useful to apply so-called advanced Fourier methods and derive pair distribution function approach, which is, in case of powders, essentially relying on two pieces of information: Bragg, that gives you the average crystal structure, and diffuse, which carries information about the deviations from the average. And then if you Fourier transform this signal and you collect it over a broad momentum transfer range, you're going to get a histogram of interatomic distances in the material, and then you can interrogate this function on different length scales and obtain information on how this behaves on different length scales. Or you can take an alternative approach. You can actually study single crystals. And so if you collect data over a broad range of momentum space in 3D, you will, in principle, get Bragg and diffuse scattering components. And the advantage of basically this is that Bragg is usually very sharp and well-defined signal, also very intense, and diffuse is rather broad and weak. And so in principle, you can either treat them together. So you would Fourier transform this entire map of Q space intensity into a direct space, and you're going to get something that is called 3D pair distribution function. Or you could separate Bragg from diffuse signal and then Fourier transform just diffuse to get 3D differential PDF, which is then actually measuring the difference in the local and the average structure given as a function of pair vectors. So to show how this methodology works, this is one simple single slide example. In this system, copper iridium thiospinel, there is a metal insulated transition at around 200 Kelvin. The high temperature state is metallic and it's cubic, where iridium, which is the main player in this system, is sitting on a pyrochlore sublattice. And then when you cool the system down, it becomes insulating and the structure changes to triclinic, where actually you have these orbital molecules that are based on iridium dimers, and they form further larger creatures such as these hexamers. So if you take this PDF machinery on powders and you go to very high temperature, 500 Kelvin, and you basically check the cubic model, you see that it actually works very well over the broad range of length scales, but it fails underneath this second peak, which is actually iridium near neighbor distance, suggesting that there is actually a local state at high temperature that has not been taken into account if you just consider crystallography. Similarly, if you do single crystal measurement at high temperature in the metallic state, you obtain these maps of very beautiful diffuse scattering that has this characteristic bow tie shape. And so, whoops, I have done it. Sorry. Thank you. So basically, this leads to precursor state that exists in the metallic regime that is a very short range, basically nanoscale precursor that relates to orbital sector, in that it's like, you can consider it as orbital liquid that is important for the system. Okay, so that being said, the main part of my talk is going to be on binary ruthenium pnictides, which are explored over the last decade in the context of superconductivity, stimulated by the discovery of superconductivity in iron-based materials. They have the same, ruthenium has the same electron count as iron, except that it's generally less magnetic. This is the state in which nominally ruthenium is. Structure at high temperature is orthorhombic, PNMA, and ruthenium is octahedrally coordinated by pnictogen and forms a 3D network of face and edge shared ruthenium pnictogen octahedra. As far as properties are concerned, ruthenium phosphide and ruthenium arsenide are systems that exhibit a two-stage metal insulated transition that is accompanied by a change in symmetry, structural transitions, and both of them have non-magnetic ground state. On the other hand, ruthenium antimony remains metallic and does not have any transitions at any temperature. Okay, so this is how the properties look like. So the most robust is the metal insulated transition at a lower temperature in all those systems. And at high temperature, you have actually a resistivity of the order of 1 milliohm centimeter. And magnetic susceptibility is Pauli paramagnetic. Now, as you cool the system down, you have this metal to insulator transition, but if you carefully look actually in the resistivity, you observe that there is a slight upturn at a higher temperature in resistivity and also slight drop in susceptibility at a temperature of about 50 Kelvin above this metal insulator transition. So these anomalies in high temperature regime are hypothesized to indicate some kind of precursor state to the insulating phase. Okay, there is also at both temperatures, there is also a symmetry change. Now, photoemission spectroscopy has not found any evidence of change in ruthenium valence across the temperature transition, which basically does not then suggest that there is a charge disproportionation in the system. And so strong charge modulation that would be accompanied in case of CDW is not seen. The other aspect is that there is a suppression of spectral weight in the UPS spectra near and above Fermi level that suggests that there is a formation of pseudogap at this higher temperature. Okay, and this has been actually confirmed subsequently in DFT calculations. Full gap at base temperature is of the order of 100 MeV. Okay, so when you now substitute ruthenium instead of, rhodium instead of ruthenium, meaning if you dope, this system starts evolving and ultimately it actually displays superconductivity in both phosphorus and arsenic variants, whereas antimony version of the material is superconducting by itself. It's metallic all the way and then at low temperature displays superconductivity. So this leads to a kind of pretty rich phase diagram where in case of ruthenium phosphorus and ruthenium arsenic, superconductivity has a maximum at the quantum critical point of the pseudogap phase. The non-magnetic ground state is pretty quickly suppressed, but the pseudogap phase persists for a longer composition. And so basically, given the difference between phosphorus, arsenic, and antimony, there is to be expected steric effects that affect the orbital overlap and also enhanced hybridization with pnictogen p orbitals. And then also rhodium doping, which is essentially electron doping, moves nominal filling from D5 to towards D6. Okay? So this is to say that this implicates the role of bandwidth and band filling into the electronic properties. And also there was an early on speculation that fluctuations of some order parameter might be relevant for superconductivity. Or you can flip this question around and naively say that maybe in reverse perspective, is TC enhanced in ruthenium phosphide as compared to the arsenic variant? And if yes, what is, by what? Okay. So the initial suspects for fluctuations are, of course, antiferromagnetic fluctuations. And this has been assessed using 31 phosphorus NMR. And so this is the map of those fluctuations, and it turns out that they become weaker as you move away from the non-magnetic ground state, and they're actually relatively weak, close to the point where superconductivity is maximum. Okay. Good. So in the high temperature metallic orthorhombic regime, there are actually electronic instabilities that are suspected to lead to this structural phase transition and electronic phase transition, and that is that both arsenic and phosphorus variants have flat degenerate narrow bands close to the Fermi level, and that states of interest that actually produce high density of states at the Fermi level are of ruthenium 4D character. And also, there is no obvious Fermisurface nesting features that are observable, again suggesting that the underlying ground state is not conventional CDW. This is the structure. So structure is essentially of manganese phosphate type. It contains, as far as ruthenium sub-lattice is concerned, zigzag chains running along the A-axis. Those are corresponding to the edge, to the phase sharing of the octahedra. And then those zigzag chains are in the BC plane connected by a ladder of distorted triangles. And what is interesting is that the shortest distance in the system is along those zigzag chains running along the A-axis. The intermediate ruthenium pair distances are actually the rungs of the zigzag ladder in the BC plane, and the longest distances are ruthenium pair distances along those straight chains parallel to the B-axis. So if you do DFT calculation that is orbitally decomposed, you can actually track that the principal instability is originating from DXY, bands derived from DXY orbitals, which are actually running along those longest chains along the B-axis. And so, okay. Since this material is relatively new, it has been speculated for 10 years what is the origin of the electronic transition. So whether it's a charge density wave or some kind of charge ordering, which turns out not to be applicable, at least not in a simple form, spin singlet formation, orbitally driven pulse transition via pseudo-Young-Teller effect, or formation of molecular-like orbitals that involve dimers, polymers, or molecular chains along the B-axis. However, at high temperature, it has been considered that this degeneracy, that is presumably the driving force, is protected by the non-symmorphic character of the PNMA space group, and that somehow all the action takes place at the transition. So the question is, what are the structures of these lower temperature phases? It turns out that they are actually not very well explored. As a matter of fact, during the work that we carried out, the structure of ruthenium phosphate was not known. It actually just was reported about 3 weeks ago. So the renormalized story goes that basically both ruthenium arsenic and ruthenium phosphate have monoclinic P21/C structure, but the structure of the pseudogap regime is still not known. it turns out that it's actually incommensurate. In PNMA structure, all ruthenium sites are equivalent, whereas in the P21 upon C, ruthenium is trimerized, such that there is 4 electrons on 3 centers. Basically, it forms trimers, like so. And so this is basically the current explanation of what is going on, again, portraying that all the action is taking place at the transition. So what happens if you engage the PDF machinery? The important motivation for that is that both ruthenium arsenic and ruthenium phosphate are anomalous at high temperature. They have basically poor metallicity, broad Drude-like component in optical conductivity, and also enlarged ruthenium ADP parameters, or Debye-Waller factors. So when you engage the PDF machinery both in the powder and crystalline form, what you do see is, for our samples, we do see both transitions in diffraction. And then when you try to model PDF of the high temperature 370 Kelvin data that is deep in the metallic regime, you see that the PNMA model works very well over intermediate and long distances, so this is the fit. However, that fit is actually giving you back enlarged Debye-Waller factors along the chain directions, U2, and so sure enough, if you take a look how that fit performs at basically for the local structure, you see that it actually fails, as if some bonds are missing. So this is a characteristic signature of displacive distortion, which you can actually, through simulations of partial PDFs, track to the distance that is the longest distance in the structure, which is ruthenium along the B-axis chains. So in order to understand this, we used as a proxy the low temperature P21 upon C model. And it turns out that it can actually explain PDF data over the length scale of 1.5 nanometers. And if you then use frozen parameters and extend the calculation to compare it to the data, you see that beyond that length scale, the model actually starts failing. So this is basically how it looks like. So the question is, what does this model imply? So to do this, we have actually carried out sequential refinements over a broad temperature range from base temperature all the way up to 370 Kelvin. And we have grouped ruthenium distances from P21 upon C model into distance groups that correspond to PNMA type distances, and this is what you actually see. You see that shortest ruthenium pairs, which are those green ones along the zigzag chains, and the blue ones, which are actually the rungs of the zigzag ladder, do not change much. However, the longest distance turns out to be bifurcated, so you get this basically distribution of distances, which is very broad. It's actually a splitting that has a frequency of basically you have two times more short bonds than long bonds, and that basically is very much deviating from the orthorhombic PNMA structure, whose bond length is supposed to be single valued, as shown by this dashed line. Okay, so another aspect is that basically there is a dramatic, whereas there is no change at all across the pseudogap transition, which suggests that this transition is disordered in character, you see basically a much larger distortion in the non-magnetic ground state, which is suggesting that this distortion in low temperature and high temperature is of different origin, that the electronic state is not exactly the same. Okay, so yes, I actually told you before what the ground state is, but when we were doing this, it wasn't known. So if you have a distribution of 2 short and 1 long distance along the linear chain, that is essentially portraying a trimer. if you do a careful assessment of other refinement parameters, such as bond angles, you realize that the bond angles on the zigzag ladder are also bifurcated, that you have 4 smaller angles that are relatively temperature independent and 2 larger angles, which actually portrays that these trimers are further organized into hexamers. Okay, so this short-range hexamer correlation is presumably fluctuating at high temperature and represents a response to the Fermi-surface instabilities in the metallic regime. How does this look like in the single crystal experiment? Well, you first observe these rich patterns of diffuse scattering that are actually quite fascinating. And then you can apply this 3D differential PDF methodology by Fourier transforming the entire map of diffuse scattering over a large box in Q space and obtain PDF. And if you do that, you essentially see here is the differential PDF, which is this red and blue signal, that it's highly one-dimensional. It's actually running along the B-axis, which is precisely pointing to the same type of distortion that we see in the powders. Okay? So if, and then there is not much signal elsewhere, which is suggesting that this distortion is really quasi one-dimensional. If you zoom in this differential signal, here you see basically a red, blue, red type of signal. Blue is negative, red is positive, which means that there is a redistribution of pair distances in such a way that both short and long distances are generated. And then another thing, if you pay attention, the signal closer to the origin is almost, I mean, it is much more intense than the one away from the origin. So to quantify that, you can basically take a cut along that direction, and you immediately see that the intensity that is closer to the origin is about twice as intense than the intensity away from the origin, again portraying a picture of there being linear trimers. So that's that. If you look elsewhere, basically the signal that we see is consistent with actually there being hexamer formations. So for example, intra-hexamer correlations, which are basically those blue bonds, are giving a blue-red-blue signal, which means that this is characteristic of strong bonding rather than that there is some kind of bond splitting. Whereas if you look into the inter-hexamer correlations, which are those basically purple, this purple signal, you see that along the zigzag ladder there are displacive distortions. So you again have red-blue-red signal, but in other directions you see strong bonding. Okay, so this is my last slide. So the comparison of density of states that is calculated for global orthorhombic and local monoclinic structure from 370 Kelvin refinement reveals that there is actually near Fermi level a splitting of the order of 100 MeV in the distorted structure. And when you do the unfolded band structure in the Brillouin zone of the orthorhombic unit cell, you also see that along this TRS direction, there is a small partial gap opening that is consistent with the splitting of density of states. If you consider structure that you obtain from the local refinements lower than 200 Kelvin, this suggests further complex oligomerization and development of 3D correlations between those long-range ordered hexamers. So that's that. Let me just conclude by saying that large ruthenium hexamer distortions are found associated with the orbital charge trimerization above the metal insulated transition and above the pseudogap phase, which presumably represents a local response to the electronic instability of the Fermi surface. And in that context, non-symmorphic symmetry protection is not operable locally on a nanoscale. This presumably represents a precursor to pseudogap behavior. And we see that pseudogap transition is order-disorder in character. and the states are, in the high temperature metallic regime, correlated over 1.5 nanometers, or 2 hexamer units. This state is electronically distinct from the ground state, which is singlet trimers. And then the question is, of course, on this phase diagram, since we are probing the regime just above the pseudogap in the parent compound, whether actually those pseudogap fluctuations embodied in this hexamer kind of object are relevant for superconductivity, meaning is it the orbital charge sector that actually is somehow involved in the either superconducting mechanism or enhancement of TC. And so with that, I thank you for your attention.
Thank you very much. Questions, please?
I would like maybe to ask what is the symmetry of your superconducting state which relates into your system? For example,
the symmetry is
of
S.
your gap and
It's a single band S-wave.
S-wave.
S-wave. So the only unusual feature of the superconducting regime is that the upper critical field is linearly increasing with temperature and does not saturate at low temperature. So it is declared to be a conventional BCS superconductor. But
more questions? It's probably not the case. Then let's thank the speaker again.